We can apply the water balance principle on a more local scale, roughly the scale of a watershed. One application for this would be to determine unknown fluxes, fluxes that we can't measure. We could also use that that's the first application. Then another application would be to say, well, we can try measuring all of the fluxes and use the water balance to check and see what the error might be. And then we might also use it to see if we find that there are errors, for example, then maybe there's a flux of water that we didn't really know about. And so we could use it potentially to identify some unknown fluxes. So the approach is going to be to basically take our system, and here I show the fluxes in a cross-section in a watershed with an aquifer. And the basic approach, remember, it's 3 steps. One is to define the control volume. 2 is to define the fluxes that cross the control volume, that cross the boundary of the control volume, as well as what's causing storage within the control volume. And then we can use that to write the balance, where everything coming in is on the left side, and on the right side we have everything going out and the changes in storage. Okay, so this is just a generic diagram. And if we want to apply the water balance principle to the scale of the watershed, then we draw a control volume at the scale of the watershed. So in this cross section, it would look something like this. So we draw it like so, and what we get then is that the fluxes that are crossing, well, precipitation here is crossing, and ET is crossing. ET is going out. These arrows here are just also ET and precipitation, so those are included. This thing, ETR, that's riparian evapotranspiration, so that's going out. This ED, that's direct evaporation, evaporation directly off the water surface. That's going out. Runoff is going out, surface water runoff. And let's see, down here, this is groundwater flow, and so we've got some groundwater flow going out. Things like recharge, it doesn't really count because that's just a flux that's within the region, is not crossing the boundary, and it's not really representing storage. So that's not going to really enter at all in this particular analysis. We also have storage of water in here. So the storage will be, well, there's water that's stored as in the Vadose zone. So we have some water here. And the water content of the soils in the Vadose zone could change. And we also could have water stored in the saturated zone, and it could change, and we could have the water table change. Say it rises like that, then more water would be stored inside of the control volume. Okay, so those are the major terms in the water balance, and we can then put them together like this. So precipitation is coming in, and ET is coming out, runoff is coming out. There's riparian evapotranspiration, direct evaporation, and here's the change in the volume stored per area stored per delta T. Now, since we're using precipitation and ET as fluxes, this area stored has to be the area of the land surface of the region that we're working with. Okay, so this is the water balance equation that we get from the previous sketch. Now, often what's done is to lump together evapotranspiration with riparian and direct, and all of those are put together and just called general evapotranspiration. In some cases, it's possible to distinguish between these 3 different types of evaporation, but often you don't, and you just lump it together. Now, this other bullet point is that the water level in the aquifer, the water content in the Vadose zone, the water level in the surface water, All these things are expected to vary seasonally. So the change in the volume stored within this watershed could vary seasonally. There'll be a time around here, it would be late summer, when the rainfall has been low and there's been discharge to the streams. The plants have been very active, and so the amount of water stored in the watershed would be lowest then. And then in late winter, after the rains have fallen and the water has accumulated in the aquifer, the volume stored would be greater. Okay, but if we were thinking about simplifying this, we could say, well, let's just take a seasonal average, and on average, we might expect that the volume is not changing. So we can take this equation here, this balance equation, and if we take the long-term average and say, well, we're just interested in steady state conditions for now, then that's going to be equal to 0. And what we end up with is this simplified balance here, that the precipitation in is equal to the ET coming out plus the surface water runoff. And indeed, this was the balance that we used and applied to the continents in a previous slide. And in general, this is the pie. So if precipitation is all the water coming in, then on average, remember the global average was 61%. So let's just say 60% to make it easy to remember. So 60%, 0.6 of precipitation is the ET, and the runoff is about 0.4 of the precipitation. So there's the pie there's the distribution of those fluxes. Okay, so that was the water balance over the whole watershed. But the beauty of this approach is that we can apply it over other regions. We can apply it over subregions. And we'll do it here over the Vadose zone. So the Vadose zone is up here, and the approach is to draw the control volume. And so in this case, as it turns out, there are a couple of places, a couple ways to draw it. And we'll do it first like this, where we've got a balance that goes here along the water table, or the control volume boundary goes here along the water table, right up here, and then the critical thing is that it's slightly above the ground surface. And so then let's take a look. The precipitation is coming in, and ET is coming out. And let's see, down here we've got this arrow here. That's the subsurface storm flow coming out. And we have also overland flow, that one right there. And right here is recharge. Okay, so those are the major terms that are going to be crossing the boundary. The storage is going to be the water content here, and changes in water content will be, at least conceptually, how we change the storage within this region. Okay, so let's take a look at how that translates into a balance. So here's the precipitation coming in, here's the ET coming out, the overland flow is coming out, this is the subsurface storm flow coming out, also called intraflow. Recharge is coming out the bottom, and here is the change in volume stored within the region over the area stored in a unit of time. Okay, so the volume stored is going to be conceptually here as moisture in the soil, and so we can have that as a conceptual understanding. And also, if we take the long-term average, then we can set this equal to 0, and we get this as a simplification. One thing that we'll do in some cases is to lump together overland flow and the subsurface storm flow, and we'll just call that storm flow. So we've got some water that's shed off of the landscape quickly during rainfall, And in this case, in this simplification here, it doesn't really matter whether it's going through the shallow subsurface and then emerging out at the toe of the slope and going into the stream, or if it's just running over the land surface. We lump both of those together, and we get this balance here. Okay, so this is a different balance than what we had for the overall watershed. That says that the precipitation coming in is equal to the ET coming out plus the storm flow and the recharge. Okay, so we can also make a pi distribution here. This pi distribution and the one that I showed you on the previous slide, those will vary depending on the area. But what I showed on the previous slide was just like the global average. And here I'm showing you an idealized case where we've got precipitation coming in, and then this pi is showing the potential outflows. And so ET is set up here as 60% of precipitation, so it's 0.6 of this area. And what I'm showing here with the pi distribution is that the storm flow and the recharge are each 20%. So that's 20% of rainfall, and that's 20% of rainfall. And this is 60% of rainfall. Okay, so as it turns out, though, this proportion is going to depend on the geology. Because, I mean, think about it. If you have an area that's underlain by crystalline rock and it has very thin soils, then when you have precipitation, a high fraction of that will be shed off as storm flow. Say you had a watershed and the entire watershed was paved, then we would have a very high fraction of storm flow and very little recharge. Okay, so in that case, the pi distribution might look like this. Storm flow might look like that. Might be all of this, and just a small little bit of recharge. Say that say around the edge of the pavement, or say through the cracks in the pavement. Okay, but if we had a watershed that was, I'm going to erase this here. If we had a watershed that was underlain by dune sand, then when it rains, we would have a high fraction of that rain soaking into the ground, infiltrating, and moving down laterally, and making it as recharge. So in that case, maybe the proportion of water that was as ET would be smaller than the global average. But in any case, there would be a higher fraction of recharge than storm flow. So let's say for the purposes of example that ET, the fraction of ET stays the same. But if we have this area underlain by dune sand, then we might expect that there would be a big fraction of recharge and a small fraction here of storm flow. Okay, so the geology is going to play a big role in how the pi is distributed, basically how the rainfall is distributed. Another approach to the water balance in the Vadose zone is to move the control volume so that the top boundary is down on the land surface. In this case, the fluxes that cross the boundary are infiltration coming in, and we still have ET moving water out. Remember, we'd have a tree, say here's a tree, and it's got some roots down into the subsurface, and so it's pulling water out from the subsurface and moving across the ground surface. We also have water flowing out from subsurface storm flow that emerges from the subsurface down at the toe of the slope, water flowing out as recharge. And we've got some water that's stored here in the Vadose zone, and that may change. So here's a summary of the balance written as this equation where the infiltration is coming in. We've got ET out, storm flow coming out, recharge coming out, and here is the change of storage. So in the long term, just like all the others, we could ignore this change in storage, and we may be able to simplify this as well. For example, if we have a flat a flat area with permeable soils, then maybe we could infer that the storm flow would be small from a particular region. So what I want to do, though, is take a look at this storage term in a little more detail. Now, if we, well, because right now we have this, it's kind of a, well, it's kind of abstract. We have the volume stored within the Vadose zone. That's this thing right here. Area stored, change of time. So how do we go about measuring that? Well, let's go back to this guy. This is the volumetric water content. And we said that was the volume of water in a total volume. That was the definition. So now over here on this side, let's go and say this is our cross section. And here's the water table. And this region above the water table is what we're considering the Vadose zone. So we have some thickness of the Vadose zone, and that thickness changes, but we could have an average thickness that would represent the entire region that we're interested in. And if that's the case, then the volume of the Vadose zone would be equal to the average thickness times the area. Okay, so if we now think of this over on this side as the average water content in the Vadose zone, that would be the volume of water that's in the Vadose zone divided by the thickness times the area. Okay, so with that, with kind of those concepts to work with, let's take a look at this storage term. That's the storage term that we wrote up there. So the change of volume stored per area per time. What I'm going to do now is write this as change of volume stored. I'm going to multiply by B, the thickness, average thickness of the aquifer. And I'm going to multiply top and bottom by B, so these two are equivalent. And what I get from that is that this thing right here is the water content. That's the average water content. Here I'm calling it the volume stored. Here I'm calling it the volume of water, but same thing. I have this delta, so what this means is that down here it's the change of the water content. So I'm going to write that change in water content times the thickness divided by time. Okay, so this is pretty cool because now we've taken it from this abstract thing up here to something that I think we can get our hands on, because water content, we can measure that, and the thickness of the Vadose zone, we can measure that, and time, what this means now is delta water content per time. We could get that by, say, measure the water content at one time, subtract off the water content at another time. Okay, so that would be a way to calculate the rate of change of the water content. We measure the water content at this time, at 2 times, basically subtract them and take the change in time between those 2 readings. Okay, so if we can measure water content, then we have a way of assessing the change of the volume stored. Okay, so let's take a look at another example. Let's apply the water balance principle to the aquifer itself. So we draw a control volume, and that's one possibility. It goes at the water table, it goes down here. This is some kind of a confining unit down below, and I've drawn this right here at the divide. So presumably there's some flow coming in from the other side, but this would be a divide, so there's no flow crossing that. But the way I've drawn this is just kind of arbitrarily out here. So this would be an outflow. Recharge is inflow. This is groundwater flowing out of the control volume. Recharge coming in, and we have base flow coming out, the groundwater that discharges to the stream. So that's an outflow. And we could include this guy here. This is riparian ET. And where riparian ET is occurring, you have plants like willow trees that are down near streams. They've got roots that can go down and pull water out of the vadose zone. So that's important in some places, but it's often ignored, and we'll ignore it for our purposes. Okay, so this would be one version of the water balance for an aquifer. Though we can change that easily. We could say, well, instead of drawing the control volume like I have, I'm going to draw it like this, where this boundary here is at the divide. So this is the groundwater divide. All of the water that flows out here on this side is going out to some other discharge point. All the water that flows on this side of the divide is entering this aquifer. Okay, so in this case, we've got recharge coming in and base flow going out. And that's it. We're ignoring the riparian ET. So that's the simplest balance on the water table. I guess also we have the storage within the aquifer, and so that may change. We could change the boundary and put it like this, in which case we've got groundwater flowing in, we still have recharge coming in, and we've got base flow coming out. So I guess the point of this is that we have these three different versions depending upon where we draw the control volume. We could have groundwater flowing in, or the first case that we saw, it was flowing out, or we could just have no groundwater flowing in or out. Often what happens is that it's difficult to determine just where the groundwater divide is. And so you might do a volume balance that is designed to determine whether you've located the divide correctly, because then the balance would tell you whether there was groundwater flowing in or out. Alternatively, you could assume that you've been able to define the location of the groundwater divide close enough, in which case you can use the simple balance that the recharge is equal to the base flow, with the base flow, of course, distributed over the area of the aquifer so that the recharge and base flow have the same units. So there are several different applications that we could set up for this balance. And here we've got it written out. Here's the recharge coming into the aquifer, the groundwater flowing in. This would be the last version that we saw. The base flow going out, riparian ET going out, and this is the storage term. So if we ignore that and we ignore the groundwater flowing in and we assume steady state, then we get this real simple balance here, that the recharge equals the base flow. Okay, so there's one more place that we want to do a balance, and that's on the stream itself. So we draw a control volume here, and we've got the flow going in as base flow, and flow coming out as recharge. And during storm conditions, we would have flow coming in as overland flow, and perhaps also coming in as a subsurface storm flow. Or we could lump those together and say, well, we've got a storm flow component coming in. So that would be the balance. Let's just write it up here, that coming in we would have base flow and storm flow in general, and that would equal the runoff. Okay, and we could also then have a change of volume stored with time. That would be due to the change in the stage of the stream. Okay, so there's a balance for the stream. What I want to draw here is another balance, and in order to do this, I'm going to look at the stream in cross-section, going perpendicular to the cross-section that we just saw. So let's say the stream looks like this. Okay, and we've got some flow coming in and some flow going out, and we've got some groundwater discharge. So this would be a flux, a base flow flux, and this would be W, and that would be L. Okay, so the balance then is that Q in, this is a volumetric flow in, is equal to, well, actually there's another flow in from the base flow. So that would be the base flow flux times the width times the length is the volumetric flow out. Okay, so that gives us a balance. This would be the volume balance, for example, over the reach of a stream. We often define chunks of streams as reaches that have some length here. And what we're saying is that the flow that comes into this reach is equal to the flow that goes out plus the flow that comes in over the length of the reach as groundwater discharging into the stream. Okay, so this will be significant because we'll be able to measure this, and we can measure that, and we can measure this and this, and we can measure that. So this will be a case where we can measure all of these, and then we can use the volume balance to see how good our measurements are.